Here's a popular exercise that sometimes gives students some trouble. What we're being asked to do is find the equation of a plane in space that contains three particular points. So here I've got points P, Q, and R. P is 3, 1, negative 8. Q is the point 4, 4, 1. And R is negative 5, 7, 2. And you'll notice that 3 points would uniquely define a plane. If you only had 1 point, you could have lots of planes that would go through that point. Or even if you had 2 points, you could have a lot of planes that would rotate around a line through those 2 points here. But if you have 3 points, there's only going to be one answer. There's only one plane that can go through 3 points like this. And by the way, I'm not saying that these points are accurately plotted or anything like that. The drawing is just for illustration purposes only. But we have these 3 points here, and I'd like to find a plane that contains all 3 of these points. So now let's think about it for a minute here. Here, if I draw a plane around these 3 points so I can kind of visualize what it would look like, let's think back, over the last few videos here. What do we need to identify or write the equation of a plane? Well, I think we need 2 things. We need any point that's in that plane, and we need the normal vector to the plane. These are the 2 things we need. Now, we actually have an overabundance of points. We've got all the points we can handle. We've got tons of points that are in the plane. P, Q, or R would suffice. But what I don't have is a vector that is normal, which means orthogonal to the plane. That means it meets it at a right angle. So that's really going to be the biggest issue we're going to have to deal with. So think about it for a minute. Can you think of a way, and pause the video if you need to, can you think of a way of finding a vector that would come down and meet this plane at a 90-degree angle with the points P, Q, and R provided? Okay, hopefully here's what you came up with. Here's a pretty clever idea, and this is really, once you get this part down, the rest of the problem goes pretty smoothly. We can create vectors between these 3 points. We can, for example, make a vector from P to Q, and we can make a vector from P to R, let's say. So these 2 vectors are in the plane. Now, do you remember something we've done fairly recently that can take 2 vectors and somehow use these 2 vectors to create a new vector that's orthogonal to both of those guys at the same time? Hopefully you're thinking of a cross product. If you don't remember it, go back and watch our cross product videos. But if you take the cross product of PQ and PR, you'll get a vector like this pink one here that is orthogonal to both of these guys at the same time. So that's going to be the process. We're going to create a vector PQ. We're going to create a vector PR. Then we're going to take their cross product. That new vector, the cross product vector, is going to serve as our normal vector to the plane, because if it's orthogonal to both of those vectors and those vectors are in the plane, then it would be orthogonal to our plane as well, of course. All right, so let me clear out some of this stuff just so we have some room to write. Here I've copied P, Q, and R just to give us some space to write some stuff down, and let's go for it. Okay, so first off, we'll create PQ, and then we'll create PR. PQ and PR. To do this, to put these in component form, we'll do terminal minus initial, as you probably recall. PQ would be the vector 1, 3, 9. Now, where did that come from? I took 4 minus 3, which is 1, 4 minus 1, which is 3, and 1 minus negative 8, which is positive 9. Terminal minus initial. Ending point minus beginning point, or at least the x, y, and z values of those points. All right, in the same way, let's do PR. Let's see here. What is the vector from P to R? We have negative 5 minus 3. That'll be negative 8. 7 minus 1, which is 6. And 2 minus negative 8, which will be positive 10. All right, so now that I have these guys here, let's take their cross product. Hopefully remember how to do that from previously in the course. So we'll take PQ crossed with PR, which will do that using a 3x3 determinant. We'll write I, J, K, 1, 3, 9. We'll write the vector PQ in the second row, and then -8, 6, 10. We'll write that vector in the third row. So this determinant will give us our cross product vector. Because it's not really the point of this particular video, I'm going to go through some of the algebra kind of quickly in computing this determinant. If you don't know how to do cross products, just go back and watch our video on cross products. Let's see, the ith component will be, let's see, 30 minus 54. So that would be -24i. And then the jth component will be 10 plus 72. So we'll have 82j. Actually, correction, it would be minus 82j. Because the 1 times 10 minus 9 times -8 is positive 82. But remember the overall signs when you're doing cofactor expansion or expansion by minors, the overall signs, you have a positive and a negative and a positive. So we're adding an extra negative here. And then the kth component will be 6 plus 24 or minus -24. So 24 and 6 makes 30. So 30k. So here's some crazy vector. Now, who is this guy? That's the guy that's going to be orthogonal to our two vectors PQ and PR, which means as a result is also orthogonal to the plane. So in our equation for our plane, this is going to be like your A, this is going to be like your B, and this will be like your C. You can use any of these points, P, Q, or R, for all I care, in your final answer. So here we go, final answer, the equation of the plane. You would have A times x minus x naught. I'll just use point P just because it's listed first, no particular reason. Minus 82 parentheses y minus 1, and then plus 30 times z plus 8 equals 0. Got to squeeze that in here. So we did x minus 3, y minus 1, and z plus 8 because it was obviously minus -8. So really the key to this whole thing here was realizing that we had to create two vectors in the plane given our 3 points, and then take their cross product to get that third vector that rose up out of the plane at a 90-degree angle. And once we had this guy, it was really all downhill from there. This was your normal vector ABC for the plane, and then that's all you needed to finish writing the equation of your plane.